Please do it that way. Bert or Cameron, either one.
All right.
Okay.
How we doing? How we doing? Yeah? Okay. When we last left, we mentioned that these percentages are fairly consistent. Now, if you've never had a psych course before, you would never know that. And that's understandable. You would never know that because it's not logical. Why would they be consistent? What I want you to do is I want you to see this data. Because I mentioned last time, finding the centers. We're smack dab talking about finding spread of data right now. But in finding the centers of the data, like we were doing before, knowing which center to use is kind of dependent on what the data looks like. If you've got a bunch of outliers, or even if you've got some outliers on one side, the average might be suspect, because the average is going to head towards those outliers. So it's nice to know, is the data bimodal? Can you tell? Now, I know I told you this data is already bell-shaped, but before I told you that, could you look at that and know that it's bell-shaped? It's kind of hard to see when it's just scattered like that, in raw data like that. So what I want to learn right now is a skill for how to make a histogram on your TI. Because this is going to come in handy from now till 244. Just be able to get a real rough and ready graph, a bar graph and or histogram, whatever you want to call it, of the data, real quick, and then how to edit it and kind of tweak it a little bit to make it more custom. Let's do that. Let's do that. So fire them up. You've already got your data in because you were dutifully entered it and got the average and the standard deviation. In order to graph anything in here, press the second button and then the Y equals button. Second, and then the button right above it, Y equals. This takes you to your plots menu. This is 83, 84. If anybody's got an 86 or 89, I'll have to sit with you after class and we'll work out the differences. You have plot 1, plot 2, plot 3, and then 4 and 5 down here you get ignored. You don't have to worry about those. How many of yours say off, off, off? Plot 1 is off, plot 2 is off, plot 3 is off. Good. I was messing with mine in 244. Anybody say on? A couple of them say on, a couple of them say on. Yeah, okay. What I want you to do, does anybody say plot 2 on? Okay, let me turn mine off real quick again. Whoops. Just right here. Okay. So press enter to access plot 1. Or press 1 to access plot 1. Either one, doesn't matter to me. So your screen should look like this, ish. Plot 1, I'm assuming yours is off, highlighted off. Just press enter to highlight on. Voila! You now have a plot on. The question is, which plot do you have on? You've got an option for 6 different charts in the TI. You've got a dot plot, or a scatter plot, a frequency polygon, a histogram, modified box plot, and NQP. All of these are freaking awesome, and we're going to learn how to do these 3 in this class and these 3 in 244. But this one right here is the one you want right now. That's your histogram. So arrow down 1, and then arrow over to it. And when you're sitting blinking on top of it, just press enter. And depending on what you had chosen originally, the bottom down here might change. Okay. Yeah, it probably changed. Okay, if you were stuck on scatter plot, you had 3, I think, marks down there. Now you have 2. Cool so far? Mm-hmm. Bueno. X list is where your data is. It calls X data. So L1 is exactly where it should be. Does anybody have anything different besides L1 in there? It probably is defaulted to L1. Cool. Frequency is how many times to use that data. If you've got raw data, that's always going to be a number 1 in that place. Okay. And you have raw data, don't you? Does anybody have anything besides 1 in there? Okay, just me. I'll fix it then. There we go. Whoops. I went the wrong one. There we go. So let's recap. Oh yeah, mine's actually an L2. Yours says L2? So if it says L2, just go down there, Madeline. Now real quick, and YouTube world, and anybody watching this video, that's kind of weird actually saying that right now. This could be watched in like 3 years. If this says anything except 1, if you want to change this to 1, notice how when you arrow down to it, it's got an alpha mark there. If you press 1 right now, it's going to change it to Y. Oh. So when you get into the list menus and you want to change them to numbers, you have to press the alpha button first and then the number. It turns the alpha mode off. It's a bug TI never fixed. TI, if you're watching this, fix that. Okay? Cool? All right, here we are. Everything's there. One thing I want you to check only because you guys just came out of Math 111. There's one thing, we'll never have to check this again. Press the y equals button just by itself. Any equations in there?
Yes.
Get them out.
Oh.
That just gets in the way. Get them out. Clear, 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 clear. Clear them all out. They just get in the way.
Okay.
They get in the way. Cool?
Wait.
Just whatever, if you have anything in any of the y1s, y2s, just get them all out of there. They just get in the way.
I'm not even on that part.
Just press y equals. There you go. And if it's empty, you're good. If not, so usually you would just be straight from here. You would then press zoom and then 9. If you press the zoom button, these are the zoom presets. Then press 9, which is the stacked zoom preset. And you should get something that looks like that. Ish. That's your data. That's your data grouped into histogram form.
Wait, should we just...
What do you got now? You getting an error?
Yeah.
What's your error say?
I don't know.
Press zoom and then 9.
Yeah.
Invalid again. Let's go back and look at what you got. Oh, you didn't change it.
There you go.
Now, 9.
There you go. Yep, you got it. We got success? Okay, good. Now that's a basic histogram. When you press zoom 9, which is zoom stacked, what that does in the TI is it automatically sets your data into 7 regions. It automatically sets it into 7 regions. It picks a minimum value and it picks a maximum value, and then it divides that range into 7, and it divides up the region using those values. I personally like to mess with those. I like to mess with those a little bit. I'm going to show you why. Press the window button. And I'm going to caveat this by telling you that you never have to mess with them. You can just use zoom 9 and be like, I got a curve, I'm done. Here's why I like to mess with them. And Tiffany, I know it's going to piss you off a little bit, I understand. Here's why I like to. When I look at these numbers right here, these are the subdivisions on that horizontal axis. The minimum value is -58, which might sound familiar. That's our smallest data point. The maximum value it shows is 34.16, which might not seem a whole lot logical. We'll come back to that. See this X scale? That's how wide each of the bars is. So press graph. Here's your histogram, right? Now press trace. If you press trace, this little spider appears, and that little spider tells you that there is one data point that is at least -58 pounds up to but not including -44.833333 pounds. Now that's hard to process. That's a lot of decimals. Now we know what that data point is. It's the -58. It doesn't tell us where it is in the list, but we know it's in there because we have the raw data. If you arrow to the right,
And we know that there's one occurrence in that.
because of this guy right here.
Right.
They use the little, I don't like the fact they use lowercase n. I wish they used lowercase f. Because usually when we tell lowercase n, we call sample size. But that would really be a frequency, wouldn't it, lowercase f? Well, something else I've emailed them about multiple times. I never got an email back from them about, but whatever. In this one, there are 3 data points that are between -44.8 and -31.7. And we can go back and find it if you wanted to. Don't. We don't have to. Just that's what it's indicating. The reason I like to finagle is because these numbers are annoying. I would like them to be much more easy to process, like rounded off numbers. So here's what I suggest. I suggest we make the bottom -60, because that's kind of a logical place to be. And remember our largest data value? Was it 21? I think it was, yeah?
Yeah, shouldn't we use the 3 standard deviation
We can, but I'm going to make sure. So you want to use that 33? Let's call it 30, if that's okay, John.
Yeah, okay.
I'm going to call X max 30, which are both extraordinarily nice numbers, yes?
So you don't have to.
You don't have to, and a lot of times you won't have this first. You'll have the graph first, you might not even have that in front of you. This one I went backwards order because the way you guys were talking, I was like, well, what the hell, let's go right to here now.
Okay.
And what am I going to scale those bars by, do you think?
10.
5.
That's 8 or 5. 10 or 5. It depends on how many bars you want. If you want twice as many bars, scale it by 5. If you want half as many bars, scale it by 10. Your choice. I was going to go with 10. That was my first gut instinct, was to go with 10. But 5 is twice as many bars. Press graph. Now press graph. You don't want to press zoom 9 again, because zoom 9 erases all this work and scales it back the way it was. If you start finagling in the window screen, you then press graph when you're done. There's our histogram. It's not as perfectly bell-shaped anymore, is it? No, but it's still bell-ish shaped. You can still see the fact that it tails off, rises, and then drops back down again. It's kind of sick. I like that. If you go by 5s, okay. There's 5s. And you can scale by essentially anything you want. I think if you try to scale it by 1, it gets pissed off and gives you an error. But you can scale by basically anything you want. It depends on how many bars you want. Notice how the scale for 5 looks very similar to the scale for 10. You've got the spike. Now, one thing that changes is over here, there's a secondary spike that gets lost with the scaling of 5. And honestly, the smaller you make the bars, and we can scale it down to say 3 if you wanted to, the smaller you make the bars, the less and less this is becoming a histogram, and the more and more this is becoming a what? It's becoming a dot plot, honestly. If you did it down to 1, it's then a dot plot. So, and that's great. That's fantastic. But you got to remember, there's a point I'm getting at to where we can't concern ourselves with that too much. It becomes, which one do you guys like the best? So of the ones we've seen, which one do you guys like the best?
10.
Do you like 10? Let's go with 10 then, just for sake of class discussion. I'm not going to force anybody to use this at all. It's just for class discussion so we're all on the same page. What I want to do now is I want to get you a visual of this thing that is called the empirical rule, which is the percentages that you guys gave me before. Where is the average in this diagram?
Isn't it the black line?
Where is the, what's that? It's a good question.
That's the y-axis.
I'm going to change that black. I wish TI would do this. It doesn't though. I'm going to change, this will make it a little more obvious what that black line is. If I do that, and I think if I do this, that's a little too close. Let's make it 12. And make this -2. What's this? That's the y-axis.
So
You will very rarely see a histogram split across the y-axis in this class. You only see a histogram split across the y-axis in this class when you have what kind of numbers? Negative and positive both. Right. Although usually the axis will be completely on one side or the other, and most of the time our data is going to be over here because most of them will be positive.
So it'll probably be like in the first and second quadrant, right?
Generally, it's always the first, second quadrant, usually just the first. But yes, Andrea, absolutely, absolutely. So there's 0 pounds. This is one reason Excel vastly exceeds the TI, is because it allows us to put labels onto our axes and see what we're actually looking at. And then these would be 10, 20, 30, because we picked it to be that way, right? Mm-hmm. -10 down here, -20, -30, and so forth, -40, -50, -60. That's kind of cool. This tells us there are no data points between -40 and -50. Mm-hmm. There we go. That's indicative. That's good. That's why going with fewer bars is sometimes better than going with more bars. My next question, I guess it was my last question, where's the average? It's at -15. Good. I like this. It's right here. That's where average is. That's where average is. It's at -15. It's 1 point. It's one data value. -15. Actually, I shouldn't even say it's not even data. It's a statistic. It's comprised of 35 data values. That's your average right there. So far now. There. Okay? So you can see right away why reporting just on the average might not be the best thing to do. For example, if the question was, does this weight loss program work? How would you answer? If this was a weight loss program, does this weight loss program work? What would you answer? Yes? On average, that's well said. On average it does. That's a beautiful statement actually. And I think we have to caveat yes with on average, because if you ask these people, it doesn't. If you ask these people, hell yeah. On average, it does. On average, we lose 15 pounds. But that's a little misleading. On average, we lose 15 pounds. Because there's a wide spread around that, and that's where that comes in. So where is one standard deviation? Where is one standard deviation? And it's one-dimensional. The average is zero-dimensional in that it's a point on the axis. One standard deviation is actually a range of values, right? And it stretches from who to who?
-31 to 1.
-31 to 1. So it would start right about here, and it would stretch all the way to about there. That is one standard deviation. And if you want, you can draw the dividing lines up to kind of break them off. When you have bell-shaped data, this is arguably bell-shaped, arguably. We'll talk more about what makes arguably bell-shaped data as we go. Roughly 2/3 of the data points. I think the percentage it's used is 68%. I think that's the one. 69's close. Roughly 2/3 of the data is within one standard deviation. We're damn close. We're off by 1 or 2, depending on how you count it. So roughly 2/3 are going to fall within that one standard deviation. Boom. That just happens. And I'll make a video to kind of demonstrate this for you more. I'll do a little computer simulation and upload that for you so you can see. Where's 2 standard deviations? Heck yeah! -47 to +17. That comes down to about here. Notice it comprises all of one standard deviation, but it goes out further. This is 2 standard deviations. So essentially, the average is in the middle. I should have let that average come down. The average is in the middle of all of these. But this guy goes out 1 up, 1 down. This guy goes out 2 up, 2 down. We got 94% of our data to be within 2 standard deviations. The empirical rule, as it's called, says roughly 95, which means roughly 95% of bell-shaped data is going to be, from here to here, which means 5% should be on the outside of that. That's what is technically usually called an outlier in statistics, that extra 5%. And since it's 5% outside, what percent would be up here?
2.
Be brave, be brave. 2.5 and 2.5. What picks up the other 2.5?
The third.
Almost all of it is picked up by the 3rd standard deviation. Not all of it, but almost all of it. We'll talk about that briefly. Okay? So 3 would be out to -63 up to 33, and I see what I did now. I didn't scale my window big enough. That's okay. We'll just draw it over to here. That's what you were getting at, John, weren't you? When you were saying use that and go outside. I think you were actually hinting at
Yeah, it
this.
was bigger.
Yeah, I should have made it bigger, but that's okay. We get the point. That's 3 standard deviations. That should pick up almost all of the data, but it doesn't. The closest decimal that it picks up is 99.7% to the nearest decimal. So that means you're missing 0.3%, which you're like, 0.3%, who cares? Well, manufacturers that make things in the millions and tens of millions really care. Because 99.7 means you get 997 out of 1,000, which means you miss 3 out of every 1,000. That means you miss 30 out of 10,000, 300 out of 100,000, 3,000 out of 1,000,000, 30,000 out of 100 million, or 10 million. So that's why, has anybody heard of something called 6 sigma? Does that phrase ring a bell? Okay, I'll stop talking about it. But what it is it's 6 standard deviations. And they manufacture shooting for that. Because now you're picking up 99.9999999, still not 100. Because there's always a chance for that goofy ass outlier way out on one end. But you're picking up even exponentially more of the data in that respect. Does that make sense? You guys buying that? Any questions? You got very quiet. It's a lot the process-ish. It's kind of about the process, but all I'm trying to say is when you have, and I'll make a video that'll hopefully wrap this up, I'll generate randomly bell-shaped data sets, and I'll keep track of the percentages, and we'll show you how they keep averaging out to 2/3, 95, and 99.7%. John, go!
So the more frequency, the more higher the deviations you're going to need to try and cover the most data possible.
Well, that depends on the data itself. This is pretty variable data. I'm sorry, I drank a lot of pool today. My voice is extra squeaky. I drank a lot of pool today. We did a lot of no-arm drills. And I consumed a couple gallons of chlorinated water. I think I'm bleaching out my vocal cords. It depends on the data itself.
So for mass production, like you just talked about, though.
It depends what you're mass producing. If you're mass producing, say, bolts and the nuts that go in the bolts, you're going to expect this curve to be like that. It's still going to be bell-shaped, but it's going to be bell-shaped like this. So you got these, hi, how you doing?
We couldn't quite hear you down at the camera.
Charlie Knapsacker, ladies and gentlemen, Charlie Knapsacker. This guy hired me. Biggest mistake he ever made.
I was literally walking up the stairs like a half mile from here and I could hear you. Like, you guys okay?
COCC will learn statistics.
Are they okay?
All of
Are they
COCC.
okay?
Yeah, that's right. All at the same time.
I'm gonna say something gay. What the hell were we just talking about? Reaching my vocal cords. Oh, right. The tolerances, it depends on what you're building. If you're building like a computer part that has to be welded onto a motherboard, very, very tight curve. Very, very, very tight curve. If you're tracking the buckshot in a shotgun shell, depends on how you scale it. That could be much, much more variable. And okay. I mean, that's the point, right? The further you get back from the target, the more that's going to spread. It depends on the data, really. We're going to attack that question in a little bit more detail in the last week of the course with the central limit theorem, when we start bridging the gap between a sample and a sampling distribution. And you're going to see that the more you sample, the tighter the curves get automatically. We'll get to that as we get through the course, though, John. You're about 8 weeks ahead of us. Danny, go.
I don't completely understand why we're using different, like the 1, 2, and 3 deviations. Like, how does that apply to
That's a great question. That's a great question. It allows you to guarantee things. Like, I know that 2/3 of my data are going to fall between these two values. So if somebody asks you, is the weight loss program working? Well, you can say 2/3 of the people lost between 31 pounds and nothing, essentially. So they lost maybe nothing, but maybe as much as 31 pounds. 2/3 of the folks in the study. That gives you that's better than just saying, did it work? Well, they lost on average 15 pounds. Okay, but what does that mean? Well, now you have a range of values to pair up with that average, but you also have a probability. And that's why I like it so much. And that's why we can identify. How many of you have ever seen one of those advertisements for Weight Watchers where they show the person that lost 115 pounds in 3 days, and at the very bottom it says results may vary. Results may vary. Results not typical.
Yeah.
So what they're doing is they're giving you the outlier, the lowest data point, and trying to use it to advertise. We're going to talk about Jared from Subway with this momentarily.
Yes.
But that's the point. They're giving you the outlier. Well, if you know statistics, you know that that's the outlier, and you know that they are essentially pushing the standard deviations out so far to capture that and ignoring the other 99.99% of the data that lost a lot less weight. You see what I'm getting at, Danny?
Yeah.
That's why you care. You care because it allows you to put a probability with the statistics.
Okay, thank you.
Oh, no! I was actually getting there because I wanted to say it ties back to what Madeline asked about 45 minutes ago, and I promised you 40, I went for 5. But that's crucial. Why else do we care? We don't care otherwise. That's the only reason we care is to assign those percentages to it. And what's cool about it is bell-shaped data happens all the time. Well, I shouldn't say all the time. It happens frequently. It doesn't happen on every data set. But many, many things are bell-shaped. And if they're bell-shaped, then you can assign these ranges and also what the range is, the likelihood of those ranges. Kind of cool. And it goes back to John's question, the tighter the tolerances, the smaller those ranges are going to be. Go ahead, John. What's on your mind?
Oh, I was just thinking that 25% of people gain weight.
That's the way we look at it, right? 25% of people in this sample gained weight.
So how good is it?
Well, it depends. On average, they lost weight. And I can say that 2/3 of the folks lost some weight. You see what I'm getting at here? Right? You see what I'm getting at here? 2/3 lost some weight. I'm not trying to sell you on this weight loss program. I'm just trying to give you the results of the study. If I was a statistician reporting on this, they'd get the graph, they'd get the summary stats, they'd get the raw data, they'd get this. And they can make there's no answer. Does the weight loss program work? There's no correct answer to that. You can't answer that question. It works for some, it doesn't work for others. We speak in terms of averages in here. We have to. Does that kind of make sense? You buying that? It's a great question. It's not a simple answer for it.
Do we know from reading this whether or not we are looking at the meal replacement
We
group
don't.
or the traditional
And
food?
I've since forgotten. You can Google it and find out. I've since forgotten who we're looking at even.
I mean, because if this is just the control group,
That's kind of crazy, actually, to think
Yeah.
about it. If the control group, which is the one that's eating just normal food, their normal diet, have
but
that
they
much
know that they're
variance.
being watched in a weight loss study.
Well, yeah, and that's the problem with randomized studies is they're random-ish-ized studies. That's a lot of syllables. But that's the problem. The idea, as soon as you start observing something, it changes. There's a name for that. But yeah, that is a problem. The quantum physics thing, exactly. Fairish? Now, here's the deal. This was a fantastic example because I was able to actually extract real data in a raw data set. That happens about 1 every 1,000 data sets that I come across, that I actually get raw data. Much, much more often, you get grouped data, you get frequency distribution data, and you have to deal with it that way. So that's why I included the next data set down. Luana, you were 45 minutes ahead of us. You were crunching it already. Look at the Portland Marathon data. Look at the Portland Marathon data. Okay? That is just a sample of some of the runners from, I forget which, it was the 2009 Portland Marathon. I should probably update that. It's been 2 years now. So this is extraordinarily common to get the results